Everybody, this is the first lecture of our second unit. And in general, this second unit, the lectures are going to be a little bit more brief than some of the lectures in the first unit. But a lot of them are kind of connected together, so we'll kind of take some time to make sure that we connect everything. And I just want to start off by overviewing our first unit in the class. And so in our first unit, we started with descriptive statistics. We talked about frequency distributions. We talked about central tendency and variability, and those were important. But then we're shifting now to inferential statistics. And we actually are going to be using things like means and standard deviations in almost all the inferential statistics that we're going to be using in the course. So the concepts of mean and standard deviation is still going to be used. And I'm just checking, making sure we're recording. And standard deviations are really important because standard deviation tells us perhaps how big the difference is between two things. And so let's say that we have two means, and let's say that we have a drug that we say treats depression, and we have one group that takes the drug, and then we have another group that takes a placebo. They think they have the drug, but there's no medicine in it. And then we compare the two on depression. We would hope that there's probably at least a standard deviation difference between those two groups to say that the drug is having some sort of effect. And so standard deviations come in handy because they help us judge how big the difference is. And this is where z-scores come from. So we don't know how big the difference is between a score and the mean. Unless we standardize it, we get a z-score by dividing that difference by the standard deviation. That tells us how big the difference actually is and where it lies on the normal curve. And so using this stuff that we just learned about z-scores and those normal curve probabilities, we can start doing inferential statistics. So I'm not going to get into likely and unlikely events right here. Right off, we're going to develop these things over the next several lectures and throughout the whole course too. So we are transitioning fully into inferential statistics. So our first topic of the second unit is sampling distributions. So I want to do this fairly hands-on first before we get into the conceptual. And so let's just think back to frequency distributions. So this is our first lecture, was frequency distributions. What are those things? So remember, frequency distributions is that we just took our sample, we took all of the scores from our sample, and then we plotted it in terms of how many people said the different scores, or how many people had the different scores. So how many people had 4 hours of sleep? How many had 5? How many people had 6? How many people had 7? How many people had 8, etc. Frequency distributions were how many people in our sample had, in this case, certain amount of sleep per night. And so a sampling distribution is similar to that, except in this case, we are going to have a population, and we are going to take different samples from the population. So different samples of the same size. So let's say we have Chaffey College students. And so we could have samples of 20. So we take one sample of 20 and we measure some statistic. Let's say we measure GPA. We take 20 people. What's your GPA? We get an average GPA for them. We take another group of 20 students. We get their GPAs. We get an average GPA for that sample. So for each sample, we'll have an average GPA for them. That's their statistic. We can plot that average. So we can plot a bunch of samples. We can take many, many samples of 20 people from the college. And we can plot the average GPA for each sample as a frequency distribution. So instead of using people, now we're using samples. And in the sampling distributions, we're examining some statistics. So I talked about average GPA in this case, but it could be any statistic. And then what we can do is we can, again, plot this as a distribution. So without talking about this more sort of in words, let's actually do it. So in class, I would normally have people actually do this, have them take out a coin. They have to usually share coins because not everybody has a coin these days. Then I ask them to flip the coin 10 times and count the number of heads. So that 10 coin flips that each person did in class is a sample. And the statistic we're looking at is the number of heads out of 10. 10 flips. So before we start doing stuff with this, what's the population value for this? So let's say that the population value means that if we did this a bunch of times, we did this infinite number of times, we flipped the coin 10 times, millions and millions of times we did this, what would be the average for the population in terms of the number of heads out of 10? It should be 5. So if we did this millions and millions of times, the average number of heads should be 5 for the population. So again, I want to reiterate, 10 flips is a sample. So every time somebody flips a coin 10 times, that's a sample. And we're going to plot the statistic. The statistic we're going to plot for each sample is the number of heads out of 10. 10 flips. So before I get into the next slide, normally when I do this, again, I would do this in class and I ask people how many flips they got. We cannot do that in person, obviously. So what I've done is I used a random number generator because your coin flip should be random. And I've just had the random number generator randomly choose a number from 0 to 10. So these are our coin flips in terms of number of heads out of 10. So the first would be 5 out of 10, 4 out of 10, 5 out of 10, 9 out of 10 heads. So we're going to use these data. So we're going to pretend these are numbers from a pretend class. And they're valid because those numbers are randomly generated, just like your numbers would be randomly generated from your coin flips. So we're going to do a sampling distribution. I'm going to actually put the numbers into SPSS, and we're going to look at 3 things. So remember the count is number of heads out of 10. So the first thing is, what's the mean number of heads? So for all of our 10 coin flips, what's the average number of heads in our sampling distribution? So those numbers we'll call a sampling distribution because, again, every 10 flips is a sample. So every number is from a sample. We're going to actually plot the distribution and see what it looks like. And we're also going to look at something called the standard error of the mean. What's the standard error of the mean? So remember that we have a sampling error. And remember that sampling error happens because our sample can't fully represent our population. So our estimates from our sample is going to be off from what the actual population value is. So whenever we estimate something just from a sample, we know it's going to be different from what the population value actually is. So if I walk up to 20 people today and ask them who they're going to vote for president, and I give that percentage to people, we know that there's going to be probably a lot of standard error there. There's going to be a lot of sampling error. Even if I go and ask 2,000 people who they're going to vote for in terms of the president, there's still going to be some sampling error. That prediction I'm going to make from my sample is going to be a little bit off. And so this concept of standard error of the mean, we're down on the bottom here, is just sort of acknowledging that. It's just saying that you're going to have some error in your estimation of any statistic. And so the standard error of the mean is represented there by that little curly Q guy. That little curly Q guy, remember, that is the population symbol for standard deviation. And it's just saying the error for the mean. So there's a little mean symbol right there with it. So all that's saying is that we can actually calculate the standard error of the mean. We take the standard deviation. I'm on the right side now on the top, standard deviation. We divide that by the square root of n. N is the number of people in your sample. So what this is saying is that our standard error of the mean is going to decrease as our sample size gets larger. That should make some sense, right? So just think about this in everyday life. The example I like to use is going out on dates. So sometimes I ask people, do they fall in love on the first date? And then I usually give some sort of little lecture that you shouldn't. But I try not to do that too much. I'll try to stick with statistics. And statistics says why you shouldn't either. Why shouldn't you fall in love on the first date? You don't know enough about the person. You only have a very small sample. You have one date. Should you fall in love with somebody after 10 dates? Well, maybe. 20 dates? Maybe. So the more dates or more time you spend with somebody, the better your prediction is whether they're going to make a good partner and whether you should be with them. So this is saying the same thing. This is saying n is the number of dates, for example. The more dates you have, the smaller the error. You're going to make better predictions about that person. So the larger your sample, the better your predictions. So this is what that's saying. On the bottom n, as n goes up, the standard error is going to go down. Your error, your mistakes are going to go down with more large sample size. You have a smaller sample size, you're going to make more errors. You're going to make more wrong predictions. So that's really what standard error is talking about, standard error of the mean. We're going to be better predictors when we have more pieces of information. We're going to make worse predictions when we have fewer pieces of information. And this is the standard error of the mean for a sample. It's the same formula. It's just saying take the standard deviation, divide it by the square root of n. N is the sample size. Number of people that's in your sample. Number of pieces of information you have making your predictions. So let's go ahead and do this. So I'm going to go to off the PowerPoint. And so we're going to start off with 10 samples. So remember that these numbers are, again, I had each person flip the coin 10 times, and I had them count how many heads came up out of the 10 flips. And so that's what those numbers are. And so these are 10 samples. These are 10 different people flipping the coin 10 times. So these are 10 samples. Let's go to SPSS and let's look at our data. And I want to make sure I'm doing everything. So we want the mean. We want the standard error of the mean. It's right here. It's a choice we can make. And we're curious about what our distribution looks like. So I'm going to do a histogram. And I have to click over. So that's the number of heads. And again, there's 10 people, so 10 samples, 10 coin flips, 10 times. So I'm going to let's see if I can make this bigger. I don't know if I can make this bigger. I cannot make this bigger. I'm going to make it bigger. I think I'm going to copy it into, and I'm just going to do it this way. I think this is the quickest way. So you see here we have a mean of 5.6 and a standard error of 0.76. I'm going to write these down. And I think I'm going to write it at the top. So let me get here. So we have number of samples. I'm going to write this down here. Number of samples. This is what we're tracking. We're going to look at the mean. So again, this is the mean number of heads out of 10 coin flips. We also have the standard error of the mean. And then we have the, oops, we have the shape of the distribution. So what does the shape of the distribution look like? So I haven't rigged this. This is just random numbers that I got. So we had 10 samples for our first thing. Our mean was, I have it actually on another, the mean was 5.6. So 5.60 was our mean. That's the mean number of heads. Our standard error is right here, 0.76. And then we're going to look at the shape of the distribution in a second. We haven't looked at that yet in terms of these data. This is exactly what I would be doing in class. And so here's the distribution in terms of a histogram. So let's look at that. What's this distribution shape? It's kind of hard to describe. Maybe bimodal. It's definitely not normal. And it's kind of hard to describe it as skew, so I'm going to call it bimodal because there's two peaks here. There's a peak here at 5, and there's a peak here at 9. And so I'm going to call that bimodal. It certainly doesn't look normal to me. So I'm going to call it bimodal. And again, I have not rigged this. This is all live. I'm just going through this. Oops, I don't need to save it. Let's add more samples. So that's our first 10. We're going to add 10 more, and luckily it looks like SPSS is going to let me cut and paste these. So again, these are randomly generated numbers 0 through 10, just like if you did the coin flips in class. They would be random also. So I'm going to add that to our data. Okay, now we have 20. You can see we have 20 samples. So 20 times we flip the coin, 10 times counted the number of heads. So I'm going to run the same thing as before. So this is for 20. So we can see that there's 20 there. I'm going to put this over here. Oops, didn't copy the SPSS. I'll do it again. Copy that. Hey, yeah, that's annoying. I'll do it again. I'll try right-click this time. Let's copy that so we can see it. Here it is. So it says 20, so we have 20 samples. So 20 times we've flipped the coin 10 times. Our average, our mean now is 4.8. I'm going to go back up. So 20 samples. Now our mean is 4.8. Our mean is kind of dancing around a little bit. Our standard error is now 0.63. So it went down a bit. Remember, we have more pieces of information. So we went out on 10 dates. For the first one, our standard error is a bit larger. We went on another 10 dates, so a total of 20 dates. Now we have a little bit of a better prediction. Our standard error of the mean's going down as our sample size goes down. And we need to look at the, I'm going to erase this, so I don't think that's valid data. And then let's look at the distribution. Okay, so it looks a little bit wild. It certainly doesn't look like a normal curve, and I wouldn't even call it skewed necessarily. It's so weird. It's kind of bi-trimodal, so we have a lot of 2s, it looks like. Quite a few 5s and quite a few 9s still. And the 8s are pushing up too a little bit. So I'm going to call this bi-trimodal, roughly speaking, but definitely it's not normal. I think we'll all agree about that. And so tri or bimodal, it's a little bit hard to describe, but at least it looks something like that. So let's take more samples. And we're going to probably jump here. We're going to add 20 more. And so I'm going to get rid of these. So we have this one, we have this one. We're going to add 20 more samples. So we're going to have a total of 40 samples. So I'm going to put this into the data, and I'm going to run the statistics again. So, oops, okay. I can go down to here. That should be 20 more samples. I'm going to add it here. And it should be 40 samples overall. I kind of want to see that down there. And there is 40 overall. So 40 times, we flipped the coin 10 times and counted the number of heads for each of those 40 samples. Okay, so I'm going to right-click this again. So with a total of 40 samples, what's our mean now? Well, it's 4.53. 4.53, I'm going to go up there. I'm going to get rid of this. I'm going to get rid of this. Lower limit. So 40 samples, it was 4.53. Okay. So we're still dancing around a little bit. I'm going to go to the top so we can see everyone here. 4.53, so we're kind of dancing around a little bit. And we have a standard error of the mean. With 40 samples, it goes down 0.50, quite a bit down actually. 0.50, maybe it went down about the same amount as before, almost exactly. So our standard error goes down, so the more information we have, we make better predictions. And then let's look at the shape of the distribution. What does the shape of the distribution look like? Well, maybe it's not as strange as before, but I certainly wouldn't call it normal at this point. I'm going to call it bimodal, but kind of evening out. I kind of feel like it's evening out a little bit. It's not as weird as before. Bimodal, but more even. Okay, let's keep on wanting to say that. Let's add another 20. So we're going to have 60 samples in total. So I have another 20 here. There we are. So we should have 60 samples in total. Let me go ahead and do this. So now we should have 60 samples in total, and we do. Let's go ahead and run our frequencies, our statistics. So this is kind of interesting. And I feel like I'm going to have to do this a little bit more, perhaps. So we have a total of 60 samples. And, oops, this is our old one. This is our new one. So we have 60 samples. So you see right here, N is 60. Our mean is 4.38. So our mean is kind of still jumping around a little bit. 438. And then our standard error is 0.39. So the more samples, the more pieces of information, we're making better predictions. 0.39. Let's look at the shape of the distribution. So they're still kind of bimodal, but it's kind of evening out, it looks like. I'm going to put that down. Even more evening out. So I'm going to, oops, I keep on wanting to do that. I'm going to pause this video for a second. I'm going to generate another 60 samples. Okay, I've actually generated 100 more, so there's 160. These are random numbers again. I just turned it off so you weren't exposed to all the time that it took to do that. So this is with 160 samples, so we add 60 more. I'm going to take this off. So 160 samples, our mean is 4.62, so now we're getting up a little bit more. 462. With this extra 100 to be up to 160, what does it do to our standard error of the mean? So it goes down 0.25. So we're going down. We're making better predictions with more information. And what does our distribution look like? I don't know if I'd call it normal, but there's not a lot of modes now. It's kind of evening out. So I'm going to say evens out a bit. And what I'm going to do is I'm going to generate another 100. So I'm going to do 260. And I'm going to pause so you don't, well, maybe you can see what I'm doing. I'll just show you quickly what I'm doing. And so there's a random number generator. So, it just gives you in general. So it tells you, this is what I'm doing. I told it it's 0 to 10. We could have 0 heads or we could have 10 heads. And I'm telling it to generate 100 numbers. And I just do this. And it gives me another 100 numbers. So just if you were flipping the coin and it's random, here's another 100 numbers. And I'm going to copy all 100. And I'm going to put that into the SPSS. So now that we have 260 numbers. And let me do that. We're way down here now. So give me a bit of time to paste that. Now we have 260. 260 samples. Each sample is 10 coin flips. So we're going to run this. And I'm going to copy this here. Sorry about that. And 260, you see? And again, we're at about 4.6. So we've kind of become a little bit more stable in our estimate of the mean. 4.6, we're pretty close now. Our standard error should go down even more. We're still going to make errors, so maybe the decrease is not as much, but we're at 0.20. So more pieces of information to better our predictions. The standard error is going down. And let's look at the shape of the distribution. It's kind of evening out still. So I'm going to say it's evening out still, evens out. And I'm going to pause this because I'm going to get more random numbers. Okay, we're continuing. I've added some more data. In fact, a lot more. And so I'm going to put the data here. Whoops. And you'll see when we go up here that I've added a lot. So now we have almost 1,200 samples. And so now we have a lot of pieces of data. You'll see that our mean went to 4.86. So almost 1,200, right, was our samples, number of samples. 4.86, was that correct as mean? I'll double check this. Yep. Our standard error now is way down to 0.09. So more pieces of data, better predictions, and then our curve is kind of evening out for some reason. I'm going to talk about this because I think I can't add any more samples to this. So we can look at this, and there's three things that happen. One is about the mean. So if we look at the mean right here, it kind of danced around quite a bit. So it was at 5.6, 4.8, then it dived down, and then started coming up a little bit. And actually, I didn't show you, but we're around 500 more samples or so, around 700. It got pretty close to this 4.86. So one thing that we notice, and I'm going to write this down, our number one observation is as we have more samples, the mean of the sampling distribution, so this is the mean of the sampling distribution. It just means the mean of all those samples that we have. So just like we have a mean for people, the people in our sample, we can also have a mean from the sampling distribution, which is the mean of all those samples. The sampling distribution it gets closer, it approaches the population mean. Remember, the population mean is 5. And we can kind of see that. There was kind of a little bit of dancing around, but when we got above 700, we started going towards 5. So the more samples we have, the mean of the sampling distribution, the mean of the sampling distribution, the mean number of heads out of 10, it starts approaching 5. You might say, well, we were close here, but see how unstable it is. It goes up and down, but once we reach a certain number, around 700, it gets pretty close to the true mean of 5. How about standard error of the mean? What do you notice? And we've been talking about this actually. So what do you notice with the standard error of the mean as we increase the number of samples? The second thing we see is that as we have more samples, the standard error of the mean decreases. What does that mean? We make better predictions. And then the third thing, which kind of didn't come out very good in this, I'm a little bit angry at this, but I'm going to just deal with it. It was kind of, if you just remember at least, it was kind of weird looking. At first, we had all this jagged stuff, and then it started evening out. Well, if we kept on taking samples, and I'm going to show you this on a video later that you can watch, it's going to get closer to normal distribution. We didn't see it really good, and I sort of gave up after 1200, but it was starting to get to look a little bit more normal. And so our third observation, which we kind of saw, I would like to have seen it a little bit better, but we just kind of saw it, and we're going to see it better in a video later in the lecture. So again, as we have more samples, we start approaching a normal distribution. I'll correct this over here. So again, this is something that we saw here in our numbers. So the mean started approaching 5. So the more samples we had, the mean of our sampling distribution approached the population mean of 5. The more samples that we had, our standard error went down. We made better predictions. And in terms of the shape, I wish we could have seen it a little bit better, but we know that the shape kind of evened out. When we had fewer samples, we had kind of weird looking distributions. But as we had more samples, it started looking more normal. And I'll guarantee that with more samples, we would have gotten a normal distribution. And so those are 3 things that you've observed in this little random number generated random flips of the coin that we saw. So I want you to remember this thing. This little thing we did. We added more samples. Our mean of the sampling distribution approached the population mean. As we added more samples, the standard error decreased. We were making better predictions. As we had more samples, our distribution started looking more normal. So why am I emphasizing all of this? It's because the thing that we just did is a demonstration of something we call the central limit theorem. So I didn't want to start off by lecturing about the central limit theorem because your ears would go off, your brain would explode, correct? So instead of telling you what the central limit theorem is, we did it. The central limit theorem says as you have more samples in your sampling distribution, your mean is going to approach the population mean. The central limit theorem says the more samples you have, your standard error is going to decrease. Your standard error of the mean is going to decrease. And we're going to talk about this a little bit more mathematically later, but it decreases. You're making better predictions. Look, we started with 7.76 and we went all the way down to 0.09. We had a huge decrease, a 1/7 decrease there. And in terms of the shape of the distribution of our sampling distribution, it looks more normal. So we might have some weird looking distributions early on, but as we have more samples, it's going to approach a normal distribution. This is kind of bugging me. I'll correct it real quickly, even though I'm going to close it. So these three things are the three major components of the central limit theorem. So I hope that when you hear central limit theorem, you don't go, oh my gosh, what does that mean? You think, oh, what did we just do with SPSS and all these random samples? We actually observed those three things. I'm going to close this. I am not going to save it. This is going to be a blank page if I need it. I don't think I'll need it though. I am going to close SPSS because I'm not going to need it for the rest of my life. No, that's not true. And random number generator, I'm going to get rid of you. And I'll go back to the PowerPoint. So this is just reiterating what we just talked about. So the more samples we have, our sampling distribution's mean gets closer to the population mean. The true value is the population mean. More samples, the closer we have to a normal distribution. And the more samples, our standard error is lower. We didn't see it as much. Typically when I run this, even in a class where we only get to maybe 100 samples, what happens is that the distribution gets tighter around the mean, and it starts looking like a normal distribution. So what I mean by tighter around the mean, and we didn't necessarily see it in our distribution, but I will show you a video showing you that it is true. So you know 100% I didn't cook the books. This was live. So if you remember our early distributions, we kind of had things like it was very jagged. Some things were up, and then we kind of went low, and then there was another mode over here, and it kind of went like this, and we had kind of strange-looking distributions that looked like that. And then for ours, we kind of saw it kind of even out, a little bit more like this. And then if we take more of the samples, we're going to see things that are getting to closer to a normal distribution, kind of like this. So you're going to see things pulling tighter to the mean. So if that's 5, there's going to be more stuff around the mean. So we take more samples, more and more are going to be closer to the mean of a 5. And it's going to start looking like a normal distribution, with more samples around 5 and fewer samples on the extreme. So that's what I mean by pulling tighter to the mean. So normally that's what you see, and we'll see that in the video demonstration, which can take more samples than I can doing it kind of slowly with you in the SPSS example. So that's the third point there. The standard error is lower. We're making better estimates, and because of that, there should be more frequencies around 5. Because 5 is the true mean, and so we're making less errors, so there's going to be more samples around 5. Not 5 exactly, but dancing around 5. So just to reiterate, sampling distributions, we take samples of the same size from a population. So for us, there's a population of, infinite number of 10 coin flips. We took samples of the same size. We took samples of 10 coin flips. So 10 coin flips was a sample, so each of our pieces of data was from a sample. We calculate a statistic. In this statistic, we had the number of heads. Oftentimes, we'll take the means. And then we start calculating those overall statistics. So remember, for each part, so we had 20 samples, we had 40 samples, we had 60 samples, we had 120 samples, etc. For each of those sampling distributions with different number of samples, we took the mean number of heads out of 5, or I'm sorry, out of 10. We took the standard error of the mean, and then we looked at the distribution. So that's what sampling distribution is. Take samples of the same size, you calculate some sort of statistic, like number of heads out of 10, and then we calculate the average number of heads out of 10 for our sampling distribution, the standard error, and we look at the shape of the distribution. That's what sampling distributions are. And that's what that's saying. You take a bunch of samples and you might look at the mean, for example. So like the example I gave earlier, so the college, we have a population of college students. We'll take a sample of 20 students, find out their GPA, get an average GPA for that sample, this sample. We'll take another 20 students, we'll find their average GPA for that 20 students. That's the sample mean for them. So each of these samples of the same size of 20 students will get a mean GPA. We know that there's going to be a population GPA for the whole college. Then we have all these little samples, their sample means, sample mean GPA. We can plot it. We did this. So remember the frequency distribution that we had? The frequency distribution was just plotting the statistic of how many, on the average number of heads out of 10. So that's what that is, and these are samples. So in this case, we can say sample means. So let's say that in this case it says N of 5, so let's say that we have the college, and we take a bunch of samples of 5 students, and for each of those students, we find their GPA, and then we plot it. It would start looking like a normal curve if we had a lot of samples. So more people would be around the average for the college. For the whole college, what's the average GPA? Well, our distribution would start going around that average in terms of the sample mean, the sample average GPA. So again, as we mentioned, the more samples you have, the more likely you're going to have something that looks like this, a normal curve. So hopefully that's understandable. We already did that. We're just repeating that. So remember the SPSS that we were looking at? It just plotted this. It was plotting the frequency distribution for how many samples had 0 heads, how many had 1 head for the average, 2 heads, 3 heads, 4 heads, 5 heads. So it just plotted all of that stuff. And again, here is our central limit theorem, which you already know. But just to repeat it, the more samples you have, the mean of the sampling distribution approaches the mean of the population. The more samples you have, the standard error goes down. The standard error, in this case we call it the standard deviation of the sampling distribution of the sample means, which is too hard to understand. I want you just to remember that the standard error goes down. We make better predictions. And then the more samples we have, our distribution evens out and starts to approach a normal distribution. And we'll get to that red point when we get to the video. So the video will show you that even if you have numbers that come from a non-normal distribution, once you do the sampling distributions and you have a lot of samples, when you do the histogram, when you do the frequency distribution for a lot of samples, it's going to look like a normal distribution, even if your population is not normal in its distribution. The video will go into that a little bit more later. And the main point of this is that it doesn't matter. The nice thing about the central limit theorem, it doesn't matter what our population looks like. We can always rely on a normal curve. That's kind of the end point of this whole thing. The third point there about the normality. Why is that so important? Well, we know if we have a normal curve, we can go to those z-tables, for example, and those probabilities under a normal curve are stable, and that lets us do research, because now we can say with certain probability how much our samples data applies to the population. If we didn't have normal, if we didn't have number 3, if this didn't turn out to lead to normal distributions, We couldn't do research because we couldn't make a certain probability statement about how much our sample applies to the population. We wouldn't know. It would change for every single sample that we had. And then we couldn't do research. So research depends on normal curves. And just really nicely, central limit theorem gives us the normal curves under 3 here. So I just said this. So why do we go on about central limit theorem? It lets us do research. It lets us do inferential statistics. Why? Because we end up with normal curves. Regardless of what our population looks like and regardless what our sample looks like, we don't care. Our sample could be not normal. Our population that we took our sample from could be not normal in its distribution of what we're studying. It doesn't matter. Because of central limit theorem, we know if we did many, many samples from that population and we plotted it into a histogram, it would look normal. Why is that important? Because once we have that normal curve, now we can use like those z-tables to make very predictable, very standard probability statements. We know for sure that our sample, even though it's small, has a 95% chance of applying to the whole population. So now we can start saying whether there's an effect or how likely there is an effect, I should say. So are we 95% sure that there's actually an effect of our drug? That the group that took the depression drug has less depression than the placebo group? How sure are we? Well, because of central limit theorem and the ability to turn basically anything into a normal curve in the end, we can use the normal curve to say we're 95% sure this difference is saying the drug works. It's not just about our sample, it's about the population, and we're 95% sure. If we didn't have the normal curve, we would not be able to say any percentages. We would just say, I don't know, maybe. But normal curves lets us say we're 95% sure, or we're 90% sure, or we're 80% sure. So I hope that you get that point. I feel like I'm sort of droning on about it, but that's really important. Central limit theorem, it's really important because normal curves are important. Normal curves lets us say things very specifically about our samples data in relationship to the population. So inferential statistics, it relies on that normal curve. It relies on those stable properties, those stable percentages that we saw in the z-tables. Again, those z-table percentages apply to every normal curve. And this allows us to say very specifically, with a percent, how much we think, we shouldn't say think, how much in terms of percent does our samples data, our samples finding apply to the population? Are we 95% sure? Are we 90% sure? Are we 80? So all of this stuff relies on a normal curve and therefore relies on the central limit theorem, and therefore inferential statistics relies on the central limit theorem and normal curves, and research does, because if we didn't have this, if we didn't have central limit theorem, if we didn't have normal curves, every single time you did research, somebody could say your sample's strange, your sample's strange, your sample's strange. You don't know how much your sample can relate to the population, so how can you say anything about people in general or about nature? Because your sample is always going to be weird. Central limit theorem says it doesn't matter. It doesn't matter if the sample's weird. It doesn't matter if the population's weird. If we keep on taking a bunch of samples from that population and we plot it in a sampling distribution, it's going to be a normal curve. Normal curve lets us make stable percentages under the curve. That lets us make clear probability statements about how much our samples data applies to the population. Hence, then we can do research. So I just sort of mentioned this. This is how we can actually do research. This is how we can make those conclusions with some statement of specific probability from our sample to population. We couldn't do research without this. And this underlies every single point of logic in inferential statistics is the central limit theorem. So just real quickly, we've already talked about this, so if you want to kind of tune out for this slide, that's fine. Just know that we take the samples data, we make predictions of the population values from a sample, so we make estimates from sample statistics to the population parameters. We saw in our example there that our standard error of the mean went down a lot as we got larger samples. So our estimates get better with more pieces of information. And basically, we've already had some of this with the mean and standard deviation. Remember with the mean, we could just divide the sum of the scores by n, the number of scores we had. Why is that? Because the mean is an unbiased estimate of the population mean, so we don't have to do any correction. And I mentioned when we did standard deviation that we can't just use n. We can't just take the sum of squares and divide it by n, because we know that these guys sitting around in basement somewhere running computer simulations of trillions of samples, that it's actually going to be off a bit if we just use n. So the correction is n minus 1. So the standard deviation is a biased estimate of the standard deviation for the population, so we have to do n minus 1 to correct for that bias. So this kind of relates to what we're talking about estimates. So sometimes we have to correct the estimate with a minus 1. So you should know this already. And so would you be able to predict a population mean and standard deviation better from a sample of 20, 50, or 100? That should be pretty obvious, right? If you have a sample of 100 people, it's going to be a better prediction of the population mean and standard deviation than if you had 50 people or if you had 20 people. You have more pieces of information. If you have more pieces of information, you make a better prediction. If you go out on 20 dates with somebody, it's a better predictor of whether you should be in a relationship with them than if you went out on one date with that person. More pieces of information, better predictions. Pretty straightforward, right? And this little thing shows us actually that we don't need very large samples to do research. So here we have the standard error. So the higher the dot, the more error. So the worse the prediction. And the closer to 0 means that we're not making any error. So we're always going to make some error, so we don't go to 0. But the closer we get to the bottom, it means it's better predictions. We make less errors. So here's the number of people in our sample. So there's 1 person, 4 people, 9 people. I didn't mean to do that, but it's not bad I did it. 16 people, 25 people, 36, etc. You can see here, just even with 9, we really are able to make okay predictions. Then we go to 16 people, our error goes down quite a bit even. 25 people, we're already pretty low. And if you notice that, there's not a lot of difference. So 25, we already can do some pretty good predictions. And then when we get to about 50 or so, we're kind of towards the end. Once we reach 100, it doesn't matter if we go above 100, it doesn't seem to really improve our predictions. So the point of this graph is you don't need a large sample size to do research. If you have sample sizes between 25 and 50, for example, you're making pretty good predictions already. So that's also kind of part of the central limit theorem. Sorry about that. I'm going to make sure it goes back. Is basically we don't need a huge bunch of samples. So this is also good news for psychological research, for example. We don't need huge samples to get relatively precise predictions. Between 25 and 50, we're doing a good job. And once you get to 100, you're actually not making much better predictions than over 65. So again, we don't need large samples to do research. And just sort of some technical notes that we'll develop a little bit more later. So, and statistics wouldn't be statistics without some sort of confusing terminology, correct? So we need some sort of terminology to say how many pieces of information are we making our estimates from, because remember, that's really important. Because the more pieces of information that we make our estimates from, the better our predictions. And actually, the better our predictions, the more likely we're able to say that our sample's data applies to the population because we're making better predictions. If we have fewer pieces of information, then we have to be a lot more cautious about saying our sample's data applies to the population because we really don't know. We only have a few pieces of information, so we're not sure. So we need to have some sort of term to note this to people that read our research. So how many pieces of information did you base your conclusions on? So that's what this is about. So whenever you see the word degrees of freedom or term degrees of freedom on the bottom there, that's what that means. Essentially what degrees of freedom means, it means how many pieces of information are you making your estimates from, your predictions from. Okay, you don't have to read all of this. I don't want to confuse you with all these words. But basically, degrees of freedom is n minus 1. So remember, n is the number of people that you have, or number of scores you have. So degrees of freedom is n minus 1. Why is that? What's the logic of n minus 1? So remember, it says degrees of freedom. So freedom means it's numbers. We don't know what the number is. It could be any number. So let's say that we have 50 people in class. I'm going to demonstrate how we get n minus 1. So we have 50 people in class. And let's say I know what the mean score of an exam is for the class. What if I knew 49 people's score on the exam? So I know the mean for all 50 people. And let's say I told you the 49 scores, so 49 people's score on the exam. Would you be able to figure out the 50th person's score? The answer is yes. If you know what the average, the mean of the exam was, and you knew 49 scores, you would be able to figure out what that 50th person's score was. So with 50 people, there's only 49 unknown scores. If you know 49 scores, you would know the 50th one. That's why it's n minus 1. So degrees of freedom with 50 people is 50 minus 1, 49. Why is it 49? Because we can't know 49 of the scores, but if we knew 49 of the scores, we would know that last person's score. We'd know the 50th. So n minus 1, 50 minus 1. So we don't know 49 of the scores, what people got, but if we know 49 of the scores, we know the 50th. Hopefully that makes some sense. So that's why it's n minus 1. Know 49, you'll know the 50th. And basically, it's just this thing is on the bottom, it says the larger the degrees of freedom, the more accurate our estimates are, and the more confidence we have making inferences from our samples data to a population because we're more confident. There's more pieces of information. So that should just remember the date metaphor. So you go on a couple dates, you're going to make more errors. You're going to be more cautious about making predictions, inferences about whether somebody should be your lifelong partner versus if you go on 1,000 dates with them. Of course, it probably wouldn't be dates after 1,000, but you know what I mean. The more time you spend with them. The more time you spend with them, the more pieces of information you have about them and how they interact with you, how they make you feel, the better your prediction is about whether you should be with that person forever. So same thing with this. More pieces of information, better estimates, better predictions. Better predictions, the more confidence we have in making inferences from the samples data to the population. I know I'm being a little bit redundant, but I want to sort of make sure that these points are clear. So remember that we have a sampling distribution when we take a bunch of samples of the same size from the population. So take 10 coin flips. We calculate some statistic. It could be a mean or it could be the number of heads. So it's the mean number of heads out of 10 in our samples. We can plot that into a frequency distribution. So we saw that in our SPSS. So we can do a frequency distribution of the sampling distribution statistic that we're looking at. And we know that the central limit theorem says the more samples we have, the more that the mean of the sampling distribution approaches the population mean. The more samples we have, we make less errors. Our sampling error goes down. We make better predictions. So obviously we get closer to the population value. We make better predictions. We can better estimate the population value. And then we approach normality as we increase the number of samples that we have. And actually also the sample size makes a difference too. So if our samples are bigger, so let's say that we took 100 flips of the coins, that would improve our distribution. That would get closer to normality. Our predictions would be better. So I want you to look at this. I'm going to change this. Yellow does not stand out well. I'm going to also post a PowerPoint. Let's do purple. Let's make sure everybody's purple. And so you can cut and paste this from the PowerPoint that I'm going to post on Canvas. So if you watch this, it's an 11-minute video from the Khan Academy, and it's going to empirically demonstrate the central limit theorem. So if you want sort of another demonstration, this one's good too because it can run many samples. So we only went up to 1,200. This one can get into the 10,000s very easily. So watch this little 11-minute video. It will reinforce central limit theorem for you. And if you want to play with the program that's in that video that was on the previous slide, here is the link. If you want to, it's not required, but if you want to play with it, here it is. And then I think this might be the final slide. This just summarizes the central limit theorem. So if you look down at the bottom, as your sample size gets larger, so it says approaches infinity. So as your sample size gets larger, your mean of the sampling distribution approaches the population mean. So the mean of the sampling distribution approaches the population mean. The standard error goes down. So the standard error is equal to this, but your standard error goes down. That's what I want you to remember about the central limit theorem. Your standard error goes down. You make better predictions with more pieces of information. And the more samples you have, your sampling distribution approaches a normal curve. Oh, I said it was the last slide. This might be the last slide. So again, just sort of hammering in, why is this important? This allows us to do research. So if we have those normal curves, so the central limit theorem says, regardless of what our samples look like and what our population looks like, if we plot a sampling distribution and our sample size, number of samples is large, we'll have a normal curve. If we have a normal curve, we can rely on the z-table, all those percentages under the curve, which applies for every normal curve. Now we can start talking about probability statements in terms of our samples findings applying to the population. Now we can make inferences from samples to population. We can do research. And the bottom part is we'll expand on this. So if you don't quite get it now, that's fine. But basically in psychology, we use this thing called p is less than 0.05. What does that mean? So just for example, we're looking at the difference between two means. Let's just start with that. That's the easiest to think about. So we talked about earlier in the lecture that we have a drug that treats depression. And so one group we give the depression drug to, and then the other group we give a placebo. There's no drug in it. And then we look at those two groups, let's say 2 months later, and we see what their levels of depression is. We would hope that our drug group has lower levels of depression than the placebo group. But we have to make some sort of probability statement about that. So how probable is this finding is going to apply to the population? So this p is less than 0.05 is we're saying that we want to say that there's a less than 5% chance that this is just random, that the drug group got a lower score on depression versus the placebo group, and it was just a chance. It was just some sort of weird thing that happened. It was some sort of sampling error. We want to be able to say that that chance of having just a random error producing lower depression in the drug group versus the placebo group is less than 5% chance it was just due to luck. It was just dumb luck. That's what p is less than 0.05. That's what it's saying. That the finding that we saw in our sample, there's less than a 5% chance that it's just due to dumb luck. It's just due to sampling error. What does that mean? That means then, the bottom part here, we're 95% sure that the drug works. We're 95% sure that this finding from our sample that the drug group was lower on depression than the placebo group, we're 95% sure that that actually is going to be seen in our population. It's not due to chance. There's 95% certainty it's not due to chance. It's probably due to the drug if we did our study right. We're 95% sure that our drug will work for most people in the population. So that's what that means. And in psychology, we use that threshold, and we're going to be using that in this class. We're going to be using a threshold of there is 5% or less chance that it's due to sampling error. It's just due to dumb luck. But that means that we're 95% sure that our finding that we saw in our sample would be seen in the population. That's inferential statistics. We can say a probability of 95%. We're sure that our sample's finding applies to our population. That is inferential statistics. And I keep on saying that's the last slide, but they keep on putting more slides on here. I should say they, it's me. I made these slides up. So I already talked about this. So the central limit theorem lets us do research. If we didn't have those normal curves, then we couldn't do research because people would just say your sample's weird. Your sample's weird, your sample's weird, your population's weird. You can't make any inferences. You can't say anything with any sort of probability. But central limit theorem derives those normal curves, lets us have those probabilities that we saw under the curve in the z-score table. Now we can say things like this. We know now that we can say for sure that there's less than a 5% chance it's due to luck. And then therefore we're 95% sure that what we saw in our sample is going to happen in our population. And I just said that. So this just says the same thing. We need samples to do research. We can use samples for research because of normal curves and because they're stable in terms of their probabilities. That allows us to say that we're 95% sure that our findings from our sample applies to our population. There's less than a 5% chance it's due to luck. We can only say that because of the central limit theorem and normal curves. And so there is no homework and there is no lab for this lecture. And what we're going to do in the next lecture is we're going to talk a little bit about research methods as a springboard into talking more specifically about how we test hypotheses. So we just went through the conceptual spine of inferential statistics. Hypothesis testing, we start doing the real work of inferential statistics. We're going to have hypotheses and we're actually going to test them. So that's it for this lecture, and I will talk to you in next.